So as promised today, I will be doing a Christmas lecture. We will build a very complex Christmas tree today. And this was inspired by the kindergarten where one of my sons is going to. Basically, they asked the kids to use scissors and paper and build a Christmas tree. And it looked something like that. So every kid with scissors and paper created such a mini triangle, a mini tree. It's a mini tree. But then they put them together like this, yeah, and so forth, and so forth. So the entire thing kind of built, I mean, except this root stuff, but basically if you ignore that for the moment, that built a complex, much bigger tree. Yeah? So the visual for that would be something like this. Here try to mimic that. So those were the little paper clips the kids were creating, and they put that stuff on the wall and created a bigger tree out of that. And why would it be interesting for databases? Well, imagine we want to query and index a couple of points. So we're now in a two-dimensional space. We have an X and we have a Y. And now we index points. Yeah? We have all kinds of points here. There's some left over from the previous lecture, it sounds like. So start again. A couple of points here. Yeah, we want to create an index on that. So we haven't talked about that yet. And that's what we will be looking at today. Because, I mean, maybe first things first. So you have a couple of points to index. You have, you have a key of type vector. That's called a vector, and it's a two-dimensional vector. Yeah, so you have two scalar coordinates. How would you index that anyway with what you know so far? A couple of two-dimensional points, how would you index that? Any ideas? Yeah? Yeah, there's one first question missing before that, before answering what kind of index to use. It's an important question to answer. I asked how would you index that? But you should now ask what? What are the types of queries? What are the types of queries anyway? So assume for a moment we only have point queries of the type. We have our get function and this key value interface, and we want to know whether this exists in the index or that exists in the index, stuff like that. So what index structure do you need to query these two-dimensional points? Point queries only. So this is like our key value store interface, which is the index interface plus point queries only. Yeah. So that's the only I'm using here. I mean, there's no range query or something like that. This is just point queries, and that implies what kind of data structure is enough to answer that? Hash table. Yeah. So hash table is enough to answer that. Yeah? Hash table. Check. Okay, so good. Hash table would be enough to have these point queries. What if you have queries along the lines that we say, okay, we want to have all points that are in this particular range from 42 to 72, where I'm not restricting the y dimension, I'm just restricting the x dimension. What kind of interface or data structure would be suitable for that? Yeah, basically I'm asking for everything in this two-dimensional region here. Yeah? Yeah? Yes, the B tree should be fine. The B tree has this interface. Maybe it's worth looking at that again. the right glasses, it's even more fun. Indexes. We have to look at interfaces, we have to look at indexing, we have to look at index, we have to look at key value store. And the key value store is combining this index with a point query mix in, but now we need this range query mix in. Now that's basically what you would be using, a minimal key to a maximum key on the x-axis. So this interface doesn't allow you to restrict both dimensions. That doesn't work here, yeah? But you could do something like that. So if your workload is like that, the B tree is fine for that. Yeah? Now we're looking at queries that are two-dimensional, x and y. You have all your points in this space, and then you specify some sort of range or some sort of descriptor as a term to use there. Actually, a descriptor. Descriptor is somehow a subspace in this two-dimensional space. It's typically a rectangle. Yeah? Could be a rectangle, and then what is the rectangle? It's making a restriction on x and a restriction on y. So it's a conjunct of these two conditions, basically. That's all what the rectangle is about in two-dimensional space. And you can easily extend that to 3 dimensions and how many dimensions you wish. Okay, that's the rectangle descriptor. And there are actually many index structures that use this kind of stuff, quad trees, quad tries, R trees, whatnot. But hey, we have another descriptor here. We have a triangle. Yeah? So we could also do something like, okay, let's assume for the moment that we have these points here. And now what I'm doing is I want to have a triangle that is big enough to cover all of these points, and I will use that as a descriptor. Okay? So that's my descriptor, and the tree I will be building will be based on this descriptor. And we will end up into something like that in a moment. Yeah? So how would we do that? Yeah, the first thing is to recall, we had briefly, I mentioned a Radix trie. Radix tree. Trie, again, is a naming invented by Donald Knuth. I know I want to show it here on my machine, actually. Use this, it's not so much scribbling here. So when talking about virtual memory, we already talked about this. And yeah, the idea of a radix, the why trie? Trie means you partition the data space, tree means you partition the data. So the partitioning function in a trie doesn't depend on the data. In a tree, the partitioning function depends on the data. If you remember the B tree, this balanced B tree thing I showed the other day, yeah, there you had to pick intervals such that you ended up with an equidepth partitioning. In a trie, you don't care. You just partition the data space no matter what the data is. And you see it here. Change the light a little bit. So this is a radix tree that's used for prefix addressing. And these kind of things are always used when you have some sort of a string. Yeah, so a radix tree is a good idea if you have some sort of string. Yeah, string could be whatever, A, C, D, whatever, B, E, F, A, D, and A, B, A. Yeah, so those are strings. They all have the same length. Well, not exactly, this is 4 digits, doesn't matter. But depending, now you can do from left to right indexing of that. You could say, I have one node, and this node splits up my data just based on the first digit. Yeah? If you just look at this one, you have only A's and B's, and then you say, whatever starts with A goes to the left, whatever starts with B goes to the right. And this doesn't have to be binary. If you have more than 2 digits here, yeah, if you had C, D, yeah, then you would have to add another subtree here, of course. So this would be B, this would be C. Okay. Then on the next level, you split again based on the second digit. Yeah, now you split up, okay, now you have ACD here and you have AAD and with a lot of AC and ABBA. Okay, now we look here at this one, which means here I have something with C, so I need a C subtree at least. I need an A subtree anyway. I need a B subtree. I said I need C, is that enough? In A, I only need C, A, B. Yeah, and then basically you would put the data here. You could put it here directly and say, okay, ACD goes here. I omit the quotes for a moment here, it's easier to write. AAD goes here, AAD goes here, ABBA goes here, and so forth. Yeah? So basically, by going from left to right, you split up the string into subtrees. Okay? Similar, in spirit, it's a bit similar to what we are seeing in the B tree. In the B tree, you also have this is also disjoint partitioning, recursive horizontal partitioning, just like in B trees. But here you only look at the domain, what's possible in the domain. You don't look at the concrete data. In a B tree, you have these intervals. Each node partitions the input into these disjoint intervals. Yeah? And the intervals are chosen based on the data you're trying to insert. Here, that's not the case. Here, you only look at the domain and the values that may occur in that domain. Of course, you can always create subtrees for stuff that's not currently present. You could also create a subtree for whatever D, E, F, G, but it doesn't make a difference. Yeah? So typically, you only create those parts of the tree where you have data for. Yeah? Okay, so that's called a Radix trie. And that's again the same thing I showed here, just a different string concept. Here the string is a binary representation of an integer. Yeah? So if you look at the slide, you see, okay, we have this 1, 1. You can interpret that as a string. Yeah? The most significant bits here, this 1, 1 of the first number, and then there's this 0, 1, 0, 0. Yeah? It's basically saying, okay, now I have these two digits, 2 to the power of 2, that's 4 possible values. So the root node has 4 subnodes, 4 subtrees, 0, 1, 2, 3, the yellow numbers. And that's basically the first partitioning step of the Radix. And then in the next level, you say, okay, now I look at that. That's the green stuff there. 2 to the power of 4, 16 different values, 16 different subtrees. Here it's 4, and so forth. And like that, you keep on building the tree. And in programming languages like C++ and C, this is relatively easy to do because you can do some bit magic on the integer, shift it to the right position, directly know the index where to go to, and so forth. So that's a very efficient tree, yeah, if you have many, many lookups. Yeah, so that's the Radix tree. So far, so good? Okay, now the next step is, okay, I have this Radix tree. Maybe I first show the implementation a bit. Where is it? So it's all in one notebook. This Christmas tree notebook also has some Radix tree here. Here you see it. So basically I have a mapping defined that the mapping has to understand how to get from this string key to a digit. So at the end of the day, a Radix tree only has these buckets, integer buckets, like in an array from 0 to n. So I specify the number of children per inner node. So I'm saying, okay, there are 2 buckets. It's a binary tree. And then I have to, whatever key I'm using here, I'm using string as a key. This stuff is coming in. I have to have a function that tells me at each level of the tree, okay, what is the bucket to send that request to? So basically, I have to look at the prefix here and then find out, okay, the first is a 1, the second is a 1, the third is a 0, and so forth. So if you do that and look at the tree, you will see, okay, we have this tree that has a root node, and each subtree splits the data by prefix into 0s and 1s, which means that all of this stuff here, all of that, is about data that starts with a 0. Yeah, that's the first subtree to the left, like on the blackboard, not on the blackboard, but maybe on the other slide, we had this, if you go here to this slide, this is basically this subtree we're talking about. All strings start with a 0. And here, everything starts with a 1. And then you recurse. So the next inner node here, this one, splits the data up again into 2 subtrees. So one that starts with 0, 0, we don't have data like that, and the next that starts with 0, 1. So you see it here in the values, everything starts with 0, 1. And the same happens here on this subtree, of course. So this is everything starting with 1, and then comes a 0. Yeah, that's the entire subtree. This subtree is everything starting with 1, and then comes a 1. Yeah, again, this node, this inner node is splitting it up again into everything starting with 1, 1, 0, and then 1, 1, 1, and so forth. Yeah, that's the Radix tree. Relatively easy concept, but used all over the place in text processing, NLP, one of the most important data structures in databases. So main memory databases tend to use these structures these days and replace B trees with that. So there are also compressed variants of that. So when you put data into these trees, you see very quickly there's a lot of redundancy, and you can do things about that, but that's a different story. Yes, you can compress them, but at the end of the day, that's a Radix trie. It's a Radix trie, and it's a very versatile structure. Okay, but now if we are in Christmas tree space, we still have to understand how to get from what we have in mind here with the triangles to a Radix tree. Yeah, and that's again an example of the laziness principle I keep on advocating. Yes? So whenever you implement it, your goal should be to understand, okay, can I map this problem to an existing problem? Yeah? Is there something I can use and that solves 95% of what I'm doing rather than implementing everything from scratch? So when you want to implement a Christmas tree, of course, a straightforward approach might be, okay, I implement all of that. I implement all, whatever, search, query, tralala, whatever, everything I will implement. Yeah? But that's not the right approach. The right approach is always to think about, okay, can I map that to an existing concept? Is there a way of doing that? And when you look at these things here, and then on the Radix tree implementation I just explained, does someone have an idea how that could work? Yeah? Any idea? I mean, if you look at these partitioning scheme, it's from left to right. There's always this prefix property in the Radix tree. Any idea?
Maybe when these triangles get more and more detailed, we proceed down a Radix tree. So we kind of specify a larger triangle with the first layer of the Radix tree. And then
yes.
Get finer in the triangle.
Yeah, you're absolutely on the right track. Very good. So kind of this triangle thing, and you see it here in this recursive drawer. So I split the first triangle up into 4 rectangles, and then you see I split all of these 4 rectangles again up into the same, another smaller 4 rectangles. It's a recursive function until you only see black on the rightmost triangle. Very good. What can we do with that? How can we map that to the Radix? Or is the Radix tree the right solution, or B tree? I don't know. So the Radix tree is really only about, let me go back to the PDF again, is only about you have buckets from 0 to n, or n minus 1, number of children minus 1, 0 to, it's a dense, it's like an array in C++, that's all you have. Okay, so we don't have triangles here, obviously, we have these numbers, because at the end of the day, you look up some stuff, and then you have a function that gives you for each of these nodes, okay, what is the subtree to delegate this call to? Yeah? And that must, at the end of the day, return such a number, an integer, from 0 to 3. So where are the integers here? Or how could you get into a world where there are integers? Yeah?
From the coordinates?
Yeah.
Decide in which subtriangle you proceed by the distance towards the points. How's it called again? Vertices.
Yeah, by distance. Actually, there are index structures doing that based on distance, yeah? Using whatever Manhattan metric or L2 metrics and stuff like that, distance-based. I think it's called an M tree. Yeah, but that's not what you could do here. So we're here, and I'm saying, and that's basically what I said here. So this is my, I have to choose a triangle for the entire tree in a way that it covers all of the points. Yeah, that's the first thing. And now I want to find out, okay, how do I map that into subspaces, so to say, or descriptors, subdescriptors. You also see that in the code. And the pattern you're seeing here is something like that. So basically, here's the middle, here's the middle, here's the middle. I draw it like that. And then I have these rectangles here. Well, I have rectangles. I can enumerate the rectangles, right? I could say, oh, this is 0, 1, 2, 3. 4 buckets. So the only mapping I need to do to understand in querying is, okay, I have a point. Which of these sub-triangles covers the point I'm currently trying to look up? And here goes your prefix. So basically, I would say, okay, when a point comes into such an index, I first need to find out which of these triangles covers that point. Yeah, for instance, if you have a point here, let's make it here. Let's assume you're querying this point. Yeah, you have to find out, okay, which of these sub-triangles covers that point. Oh, that's 3. Okay, so the first digit is a 3. Oops, boom. Yeah. Then, when you recurse, you look at the sub-triangles of this one. Use the same numbering recursively. So I remove the 3 here. The entire thing is a 3, of course. But if you look at the pattern here, 0, 1, 2, 3, I could write that again here in the sub-triangles, whatever, 0, 1, 2, 3, or something like that. And that's not inverted, yeah, of course. Then, okay, maybe that gives me the next digit, 2. Yeah, so basically, these digits describe a path through the tree, describe a path through the recursive partitioning function. And that's a property of Radix trees. You see it here already. If you have a string, these strings basically are like, they're like Google Maps in a way. They describe how to traverse the tree. And they tell you, okay, so in the root node, you first go to B, and then you go to E, and then you go to F, if these levels exist. Huh? But for instance here, for whatever, for A, C, D, this, okay, we first go to A, this one, then we first go to C, this one. There's no further split up here. We already reached our destination. Yeah? So these are paths through the tree. And that's what will be exploiting in the implementation. So whenever a point comes in, I just check at level by level, does it cover this specific triangle? And if that is the case, I delegate to the subtree. Okay, so the Radix tree we looked at. I think here we have to look a little bit at the implementation. Oops. And one thing to understand here is this, did I put it in utils? I put it in utils. So there's something like a triangle now, here in utils, and that's described by some linear algebra. So I just have this support vector A, and then, maybe I put it on the blackboard again. So I have a triangle, and then I have a vector A. That's basically A, B, and C. Yeah, that's all you need to describe the rectangle and linear algebra. So AB is relative to A, of course. That's the edge from A to B, or the vector from A to B. And this is a vector from A to C, of course. And then I have a couple of computations. But the important thing for our index is I have a method that splits an existing rectangle into 4 new rectangles. So here, for instance, triangle 1, lower left, says, oh, it's the same support vector as A. Yeah. However, AB is half the distance. AC is half the distance of the original AC. Here goes my first triangle. Yeah? And so forth for all the other triangles. So I have a top triangle that is A plus AC half. Yeah, so A is moved by AC half. That's this one. And here it's this B is just the half of AB, and AC is the half of AC. Here goes my other triangle. And the same I do for this one. And then the middle, the different ways of doing the center triangle. What I do is A plus AB half plus AC half. What is that? That is, so this plus that plus that. So I'm here, and now I'm going backwards for the other triangles. You could also define it differently, but that's basically what I'm doing. So that's the final triangle here. And that is used in the tree. Right. I also have then here a check to see, to compute the center. That's more for visualization purposes. Yeah. Okay, what else can I show here? Maybe look a little bit at the Radix tree. So when you go to indexes, there's now Radix trie. There's this key mapping. That's basically what I explained. You have an incoming key, and you have to return a bucket where that key belongs. And that's basically another strategy pattern I'm using here. Then the actual Radix tree, or trie, is the key value store, of course, as usual. And then it's the same pattern as in B trees we have seen. There's some sort of abstract node. The abstract node, again, is the key value store. And then we have inner nodes and we have leaf nodes. Inner nodes are exactly as explained on the board. The leaves just keep a list of the values, like here. Yeah? So if you have a leaf here, so you don't further split up, you just have a Python list of all the key value pairs you insert into the leaf. But again, the leaf is a key value store, of course. Other than that, it's a couple of show and draw and whatnot methods. Get Radix. That's the helper method determining the Radix, basically. But actually, it's a two-level process. In that, so going back to this laziness principle, the insight is really, if you have any of these descriptors or recursive descriptors, you can map them very easily to a Radix trie. Did any of you ever see space filling curves? Like Z-codes or something like that? Yeah, because, of course, no one would use triangles in practice. Not so common. But there's another very famous concept that's called the Z-order curve. And it follows the same principle. And if you use this kind of descriptor and this kind of mapping, you could again map that easily to such a Radix trie. So maybe just the helper functions also. This is a similar mapping of a data space. If you look at that, you see, okay, this is again a recursive mapping. Maybe I break it, maybe I think if I do it a 1 here, yeah. So if you don't use triangles but use rectangles, yeah, and always split the data space recursively into 4 subrectangles. This method is actually super common in computer graphics. Also geographic information systems. Okay, then you can number those things. You could say, okay, this is 0, 1. This is 1, 0. And this is, no, other way around. Ah, come on. 0, 0, 0, 1. 1. Yeah? So you have 4 numbers to enumerate that, and that's what you see here in this notebook. And now, if you recurse, so if you split each of these regions again with the same scheme, look at it, this is like a pattern, a partitioning scheme that you can apply on any of the recursion levels. Yeah? Now let's increase the recursion level. You get something like that. You see the red stuff stays the same. The prefix is untouched. Yeah? So within this block of the first numbers, this number and that, it's still all zero. Sorry. And this, it's still all zero, red zeros. But the green stuff is again applying the same recursive partitioning within this stuff. And if I did that here, that would mean everything starts with 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, and so forth and so forth. So you could map that easily as well to a Radix Trie. And this leads to something that's called a linearization order, or in this example, a Z-curve, a Z-code. Why a Z-code? Hard to see, right? But if you increase now the recursion level, you see an interesting geometric pattern that occurs. So this is basically the linear order through these numbers. So once you did this partitioning, you can enumerate them in the one-dimensional space, yeah, along the numbering. And if you draw a curve through that, that's what you get. Yeah? If you go back to the first recursion level here you see it. So this is the numbering 0, so 0, 1, 2, 3 in binary. Yeah? And then you keep on adding another recursion level. And then if you see here's the numbering again. There's a small z, another z, another z, another z. And of course, the z's of the different regions are connected. So you still have on the top recursion level, there's this order. Yeah, there's still this big Z basically overlaid with that Z. Yeah? And that's basically how you get this Z order. Yeah, and then you keep on recursing on that. Yeah? And there are many, many examples for these curves. Hilbert curve is another example. It's actually a fractal curve. It has interesting properties. One is that the dimension is not 1 or 2, but in between. It has a fractal dimension called the Hausdorff dimension. It's very fancy properties. For indexing, it has an interesting property. So if you do something like that, and you're too lazy to implement a Radix tree, Christmas tree, whatever, but you have this linearization. Does anyone see what you could do with that? Yeah, again, assume you want to index 2-dimensional points. Again, these curves also work for higher dimensions. Assume it's 2 dimensions, but what could you do? Yeah, your keys are 2-dimensional. And now we have this curve. You have a function that given each 2-dimensional key, it computes the Z-code. Yeah? What could you do with the Z-code? The Z-code, or the result of the Z-code, the domain is 1-dimensional. I have a 1-dimensional domain, so I could put this 1-dimensional Z-codes into a B-tree, which supports range queries. Now, what you could actually do in these things is you can do 2-dimensional range queries as the ones we had here. You have a rectangle being specified. For each, for the rectangle you have here at hand, you transform the rectangle into Z-codes and transform that into a 1-dimensional interval query. And then you answer the 2-dimensional query with a 1-dimensional tree. Yeah? It has some problems and flip sides. Longer story, yeah? But just for you to know, this is another example of simplifying a problem, saying, okay, I don't care about a higher dimensional space, I map it to a lower dimensional space. And the machine learning people do that all of the time. Yeah? If you heard about embeddings, that's basically the same thing. It's reducing, it's transforming data from a higher dimensional space to a lower dimensional space, and then gives you interesting insights. Yeah? Well, one interesting property here about these curves is that they tend to preserve spatial proximity in most of the cases, not in all. Yeah? But if you look at the data here, you see, okay, yeah, if these points are close in two-dimensional space, they're kind of close most of the time also in this Z-code space. There are extreme cases. Yeah? Of course, here, this point, for instance, what did I want to show? This point is very close to this one in two-dimensional space, but not so close in the linear order. So there are exceptions. But statistically, there's a high likelihood if you're close in two-dimensional space, you're also close kind of a linear space. And that maps very well to B trees. Okay, so back to our triangles. And now it's time, so I basically implemented such a Christmas tree. The Christmas tree for me is just, okay, it has these triangles. I should, no, this is a text version still, okay. So now what I have is, I have these descriptors all over the place. Important for you to understand is, actually you don't need to store the descriptor here in the root node. So for each of these trees, the only type of descriptor you need to know is when making a decision to which subtree to go. Yeah? So when you're in the root node here, that's the root node, and now I have like 4 subtrees in my Christmas tree. Yeah, so you will see that in the output, there's a descriptor here. The descriptor is this overall rectangle of the entire data space. You don't need that for the actual index structure. I just need it for the visualization, because otherwise the visualization would look stupid. Yeah, so I have an additional descriptor here, but it's just for visualization purposes. The only thing you need here is these 4 subdescriptors, allowing you to route the incoming request to the right subtree. Yeah, so there's a small rectangle here, here, and then there's this middle rectangle here, something like that. And what the implementation does is, it goes through all of these descriptors, always in the same order, from left to right. So you have a fixed list of these descriptors, and the first that matches will be returned. Yeah? So I go through that, oh, it doesn't match, the point is not contained, check that one, oh, the point is contained, I go on here, go to this subtree, and then I recurse and recurse. Does anyone see an implication of that, and a difference to B trees? Yeah, from left to right, I check these descriptors. In this case, those are triangles. And if I do it like that, I get something for free, which is really cool. Are the subdescriptors disjoint? Do they have to be disjoint? I mean, if you have a visualization like that, and the point happens to fall on this line, you want to make a decision, okay, if I have points like that, do they belong to this rectangle or to the middle rectangle, the big middle rectangle? Yeah, so we're here. Yeah, the point happens to be there. If it's a disjoint partitioning, like in the B tree, you have to define at some point, does that point belong here or does it belong there? Because otherwise you might get into trouble in querying. Yeah, if you have like binary search or whatever search method on that. Yeah, so do we have to have that property? Do our subdescriptors have to be disjoint? I always use the same order from left to right. The first hit, the first match will be used for query processing, no matter whether it's a put or get request. Yeah? So if you had, assume you had 2 descriptors like that. Those are my subdescriptors. So when would I go left? When would I go right? Yeah? So those are my 2 subdescriptors. I start checking this one. This is my first rectangle to check, and that's the second. So what happens with the points here? Yeah? They always go to the left. I don't have to worry about this stuff. It's still correct, because even for searches, the same thing will happen. Yeah? I will just assign everything that's in the intersection of a descriptor to the one I check first. Yeah? So that's again, oh, whew, I don't have to worry about this stuff anymore. It's just the order will fix all of that. Actually, I made it half open at some point, but then there was a bug, and I wondered, why do we have to make it half open? It worked like that anyway. So you see the sub-triangles are fully closed regions geometrically. Yeah? So the line belongs to this one and to that one at the same time. Still, by doing that, I don't care. It's still correct. No. Okay. Yeah, and then you see, yeah, you see how such a tree looks like here. You have these descriptors, you have inner nodes, and then the data partitioned accordingly. Yeah, you see these sub-descriptor triangles here, and so forth and so forth. Yeah? So it's a relatively large tree. Oh my God, what am I inserting here? Okay. And here's the first visualization of what we're seeing here. So some lametta, however that's called in English. And what is the lametta? Can you map that to any concept we've learned about so far? Yeah?
It's the Z-curve pattern, but with triangles.
That's the Z-curve pattern, but with triangles. That's correct. Yeah? So the linearization order of the triangles of a certain granule. So you're seeing it's not on the smallest triangles, it's always in the center. If you look at the centers, you understand, it's these inner node triangles. Okay, yeah. That's correct. Can you map that to a concept we had in this lecture so far? Where would that pattern, where's the linearization order in indexing? A tree is a tree. Is a B tree a tree? That's a good exam question. Is a B tree a tree in the sense of a data structure? And the answer is of course not. Why not? Why is a tree not a tree? Yeah, it has these connections between the leaves. Yeah, so as the leaves now describe these descriptive things, yeah, what we're seeing is basically this isom property across the leaves. That's what I'm visualizing, and that's my lametta. Yeah, so it's basically what you could use in a linear scan over those leaves. Yeah? So space filling curve over this Christmas tree, and if you see it, it's a two-level space filling curve. So we had when we looked at this how the triangles, the sub-triangles are defined. You see. There's always this pattern. Bottom left is the first triangle, then the top right, then the rightmost, down to the right this triangle, and then the center triangle. You see it here as this mini pattern inside here. And that happens recursively, of course. So the big pattern, you see it's always this overlay of the two curves. Is this one, this one, this one, that one. Yeah? And within such a bigger triangle, you have the partitioning into smaller ones. So you first do this, then you jump here, do this, you jump here, you do this, you jump here, you do that. And in the implementation, you see that in the inner nodes. Sorry, not in the inner nodes, in the leaf nodes. Yeah? There I can specify in the initializer a left sibling. That's what I'm using when building the tree. I create this connection among the leaf levels, and that's basically what happens here. And if you specify such a leaf node here, that's basically done in the draw method. So this draw method draws a node or leaf to this canvas that you're seeing in the Jupyter notebook, and if a left sibling is set, then basically I draw such a stroke line in this golden color. But again, this isom line in two-dimensional space is really a space-filling curve. It's the same concept. Okay, yeah. Now let's animate the tree a little bit and make it a bit richer because it doesn't really look like a Christmas tree yet. So a couple of things missing. So let's start with what we have here. Syntax error. Oh, maybe I should also comment this. Right. Oh, come on. I should not comment this one. That makes sense. Yeah. What's wrong here? No, this is still okay. That should be gone. I still have 2 of those. That's a bad idea. Ah, here we go. So, so we had some snow. So in the following, what you see is, and again, that's done through factory methods. So I have different extensions of the tree. So I keep on, in the implementation, I keep on extending the inner nodes to do more stuff, or the leaf nodes to do more stuff. And I parameterize the tree by injecting a different node factory here. This can be configured by passing a parameter. So it's always the same node factory for vectors mapping to a string value, and I can add some stuff here to visualize more things. Yeah? And this thing, what it is doing, it's just adding snow. What is the snow? This is the points that are indexed by this tree. So each point is just visualized as a small dot. And implementation-wise, what you need to do is, when you're working with Canvas, so this Canvas library is really super useful to visualize all kinds of stuff in Jupyter Notebooks, but sometimes it overwhelms Jupyter, and then you have to play this trick to use this withhold canvas, and that will first create the graphic internally, and then once it's done, display it. So I create a number of trees here, and I keep on adding more and more data. So this inner loop, what this is doing is it's really just adding more data, more random vectors to this tree. Yeah, and the cheap trick I'm playing here is I create a random vector, in a square space, and then I check whether it's contained in the triangle, and only if it's contained in the triangle it will be inserted. Otherwise you draw another random point. You could also parameterize that if you wanted to just draw from the triangle space, of course. Yeah. Right. And now we keep on adding this. Yeah? So now we need candles. So what are my candles in this tree? I use a different factory. And then you see there are kind of candles, and they're moving up and down. That's not what the candles on your Christmas tree back home is supposed to be doing, but it looks a little bit like a candle. And here's an alternative visualization where I show the different... Oh man, why isn't this one line? I wanted to show the inner one. So basically I'm spelling out the different stages of the trees after a certain batch of vectors I'm inserting. And now if I do this with the candles, it should look like that. So you see, okay, there are candles, okay, they're burned down, but then they're replaced by new candles, which are very tall again. What the heck are candles in an index structure and in a tree? And this is one of the most important tricks in indexing ever, those candles. So we had a joke in my group that who would be reviewing this paper. So this is reinvented every year. Someone reinvents this technique because it's so extremely powerful. And you see it all over the place in different names. Yeah? So what is that? Candles. And this goes back to a paper by a guy called Lars Arge from the 90s. It's called a buffered tree. 11, 10. So in the standard Radix tree, or whatever tree, this idea applies to all index structures. Yeah? So you have your nodes, whatever. Yeah? Some tree structure. And now what a buffered tree does, or buffer tree, don't exactly remember, buffer tree, is it piggybacks on top the idea that for each inner node, you add a little buffer with operations. That means that's my candle. I even have red color here. Almost red. That's my candle. And what that means is for a put operation, typically, okay, if you call put, you immediately run down the tree. And I'm departing from that. Now I'm saying, okay, if there's a put, there's a buffer of, let's say, whatever, 5 operations, 5 put operations. And if there's room in the buffer, I first put it into the buffer, the key value entry. I don't push it down the tree, but I keep it here. And the same happens recursively. Yeah? Only if the buffer is full. So if you happen to put something here and the buffer is full, you flush the buffer, and that means you look at each entry here of those operations and flush them down to the appropriate subtrees. Yeah? So that's also again like a recursive partitioning. We talked about that before. So basically, rather than tuple by tuple or insert by insert, putting it down to the leaf level, you first collect the stuff and then you push it down once the buffer overflows. And there's a poor man's version of this method that's called differential indexing. And that's basically what is reinvented every year. The buffer tree is not reinvented every year, but differential indexing at least once every year. And we were joking about that, who would review the differential indexing paper this year. And it was really funny because for a couple of years I'm also reviewing for conferences, and then there was another paper, hey, we invented this super great method, that is fantastic. They didn't call it like that, of course. Yeah? Maybe they didn't know about the paper that invented that 100 years ago, but they had something similar. Yeah? And the idea is really that when you have insert operations, you don't send them directly to your big index, but you collect them somehow, either in a small index or in some sort of buffer. And only if the buffer exceeds a certain size, you put them into the bigger index. Yeah, this is basically a one-level application of this idea. Here you apply it to each and every node. So this is a much more generic method here. Yeah, see the difference? Yeah, here's just one buffer, that's my candle in a way. Yeah. That is the candle there. There's another class of methods, indexes, that's also, there's so much research on that, that's called log-structured merge trees. Log-structured. And you see that in real products. You might bump into that later on. Log-structured merge trees. What is the idea? You have something like this. You have a cascade of these indexes. Yeah, because the problem here is if you have this super big index of a petabyte or something like that, and then a couple of megabytes, and every time you merge into the petabyte, it's still a lot of work. And you can amortize the work by having a cascade of indexes that gets smaller. And if this overflows, you don't immediately merge with the biggest, but you merge with the next. If that overflows with the next and so forth, you have a cascade through these indexes. It's called log-structured merge trees. Zillions of sub-indexes available there. It's all the same idea. It's those buffers. And that's what you see in the visualization here. So whenever you run the visualization, I have buffers. Maybe look at the code a little bit. I think I did it on the Radix try level, but on the Christmas try level, but you could also do it on the Radix try level directly. So I have this buffered inner node. Yeah, this extends the Radix try inner node we had so far. I specify a buffer size, and then I initialize. I mean, here you don't have to specify array of size, max buffer size. We're in Python. You just say, okay, that's my max buffer size. I have a list of key value entries. Those are the operations. And then when you have a put operation, okay, if the len is greater than the max buffer size, then you flush. Yeah, then you push the stuff down. Then the candle shrinks. The candle is removed in the visualization. Huh? What? Okay. Something funny? So yeah, shown for educational purposes. That's not how to do it. Yeah? Okay, so that's what I said. Whenever there is a is subclass or is type check in your code, you're getting object orientation wrong. I'm just showing it here for educational purposes for you to understand how not to do it. If I only show it how to do it the right way, you don't learn. So I also showed some errors. Yeah, twinker, twinker. Yeah. I was just too lazy to add another polymorphic method. Yeah. So this is, you will see that in a moment I can flush all the buffers at the same time in the tree, and you see that all candles will disappear. Yeah, so don't do stuff like that. Whenever there's type checks, think about it twice. Okay, so put, yeah, here you put, if the buffer is full, you flush the buffer down, and then you append to the buffer. Yeah, so there's no rerouting to the, direct rerouting to the children underneath. And that means for get, of course, oh, hey, if we have get, now we have to be careful, right? I mean, because it's, you always, at each of these nodes, we have to check, maybe the entry I'm looking for is in the buffer, plus I still have to reroute to the tree underneath. It's the same thing as before. In addition, I always check the buffers. Yeah? So that's what's happening here. So I filter the buffer with an iterator, check whether the stuff I'm looking for, the key, is in the buffer. I map the results to the values. That's what this map operation doing. So this gives me an iterator of the values that match my key from the buffer. In addition, I have to do the same thing as before. There's the same get method as before. In other words, I call it super.get. That gives me this traversal of the tree. And what I return is the union over the two iterators. And this is, in Python, you can do that through chain. So chain is just saying, okay, this will return an iterator that returns the results of both of these iterators. That's what I'm doing here in the inner node level. Yeah? So basically what you would expect. Yeah? And then you can reason all kinds. You can make cost models and complexity analysis over those buffers, how you change that and factor in main memory and adjust sizes like crazy. There's a whole sub-area of databases just looking at these things. Yeah? So these things are used in products. I mean, the most prominent use case for differential indexing used to be search engines, textual search engines like Google. Yeah? If you think about how to index text, you will see that whenever you add a web page, you have to touch many places of such an index, and you will get crazy. It's super inefficient. Yeah? And that's why they had something like that. Differential indexing used to be the most efficient technique. I think you don't have to use it these days anymore, but yeah, that's the way to go. So it occurs all over the place in different names. Yeah? Just remember, buffer tree, differential index or differential file is another name. Log structured merge trees, you will see that at some point or the other, because it amortizes a certain costs, and basically it's again another pattern, a batching pattern. Yeah? So rather than doing things one by one, you form groups of things, and then you perform operations for the entire group at the same time, and then you gain, of course. Yeah? Good. What did I want to show? Yeah, this buffered inner node. Right, yeah, and then again, so in all these node extensions you see, I always reroute to the underlying operation here. I reroute to the draw operation, and then, okay, I have to draw these red rectangles. That's what I'm doing here, and that's basically the buffer. Yeah? So the buffer, the size of the buffer is basically, the length of the buffer symbolizes the size of this candle, and that's all I'm doing here. So let's look at the width again. Yeah, then basically what you're seeing here is, okay, yeah, there's a lot of, many of these buffers have to be, once the buffer is full, you flush it down, and then, of course, I think it's better to see if you round it out, right? Not really. I think I have to make it slower. I just invite you to play with these numbers a bit with the batches, and then you see the pattern really that happens in this tree. Okay, let's flush all buffers. Yeah, that's what you see. That's this method, this hacky method I inserted into the code, and here you see, okay, the buffers are all gone, they're all empty. I mean, they're still there, but they're all empty, and that's why there's no visualization whatsoever, and then you see it's just all these dots. Okay, one other concept I want to add. So let's change the factory again. Get it right this time. Here we go. So we have these, I don't know, Kugeln, balls, these shiny balls that you put on your Christmas tree, and you see them, or they have a very clear color, and now they get lighter and lighter and almost disappear in this tree. And again, I will try to roll it out a little bit. So if I show the different frames here in this visualization, you will see what happens. Aha, so initially they're very visible, and then they get lighter and lighter and disappear. So what are those crystal balls here? That's another thing I added on top in the implementation, and that also appears like everywhere. To put it on top of the buffer tree. You could do it without the buffering, of course, and maybe that's the reason for putting a separate drawing here. So I have a tree. I ignore the buffers for the moment. And now what I have is a little oracle, a little predictor telling me, okay, there's a method coming in. Could you please predict, that's a crystal ball, yeah? The magician looking into the crystal ball. Oh, do you happen to have a key like that? Is it worth running down the entire tree anyway? Yeah, that's the idea. So that's my crystal ball. So I basically, before running down the tree, before making a decision to which subtree to reroute my get or put request, I first look at the crystal ball. Hey, dear crystal ball, can you tell me whether there's something, whether it's worth looking down in the tree? And only if that is the case, you do the the magic you did before. Again, recursively. Yeah? And how does that work? Well, if you remember what we did on Wednesday, you could attach a bitmap. For instance, you could say, if your search space, or if the key domain is an integer, yeah, and you have whatever, you have integers from 0 to 0, 1, 2, blah, 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 blah. Let's say it's only whatever, 4 billion or something like that, 4 times 10 to the power of 9, you could easily create a bitmap of that length. Yeah? You could say, okay, I have a list of 4 billion Boolean values, right, and attach it to every node. Is that a good idea or not? Attach 4 billion bool values, 4 billion bits, each signaling whether the key, whatever, 42, 42 exists in the tree, this bit will be set to true. If 42 doesn't exist, it's false, so I can attach the bitmap here and this bit list here, yeah, and if the bit is set to false, I don't have to continue my search. Is that a good or a bad idea? Hmm? 4 billion bits. What if my key domain is 4 to, or whatever, 10 to the power of 14? I create 10 to the power of 14 bits and attach that to this root node? Are you kidding me? That's a lot of bits. So depending on how many keys you have, this is insane, right? So this is something using the bitmaps we learned about so far. It's a good idea if your key domains are small. Yeah, if you only have 4 different values, yeah, okay, yeah, then that's a good idea. But what is the technique to use if the key domain is big and you want to map it to a smaller key domain in computer science? What kind of hash function? Yeah, that's the main motivation of using a hash function. You have crazy keys, but you have only little memory. So you only create little memory, like from 0 to n-1, these buckets, yeah, and so forth. And rather than using the key that comes in directly, you first pipe the key through a hash function. Yeah, the hash function gives you a bucket, and there you insert the stuff. That's how any hash table works. Okay, and now we use that here for a filter. So the filter I'm creating also uses the hash function. So rather than creating a zillion bits, and by the way, I have a different problem here. I mean, I have two-dimensional data. I mean, how would I even create the array here? Would I create a two-dimensional array? I mean, no, probably not. So I need a hash function where I can send a vector. Yeah, that's my vector, well, my point. And that gives me a bucket. Yeah? So for every point, I will assign it to a bucket. But now I don't put the data there itself. I don't put the points there, but this array is of type bool. Each bucket is of type bool. Okay? Yeah, so I have a bool array here, and that says 0, 0, 0, 1, 0, 0. And now what I do is, and that's the implementation of the crystal ball, is, okay, when a query comes in, so we're here, and this is, again, the query is get of a particular point. Yeah, get whatever, 4.2. Yeah, that's my key I'm specifying. I pipe that through a hash function, and the hash function gives me a bucket, and the bucket is telling me 0. What does that mean? At that level. Yeah, crystal ball is telling false. What does it mean? What's the semantics? Yeah?
I think if the check says no, then you're sure that it's not in there. If there's nothing with this hash function, but if it says yes, then you're not sure. There could be flashes, so there could be other elements of the same hash function, so it doesn't have to be.
All correct. Yeah, so if it's 0, the semantic is it's guaranteed to not be there. Otherwise, it would have been set by a previous put operation. Yeah, the hash is consistent, the hash function, yeah? Or it should be consistent. Yeah? So if you had put in 4,2 before, piped it into the hash function, it would have pointed to the exact same bucket. You would have set it to 1. So you would see a 1 there. That's case 1, that's easy. So it's an exact information saying, no, it's not there, it's guaranteed to be not there. However, it's set to 1. This only means it may exist. This is also why this is called a probabilistic data structure, because this 1 could have been set by another insert, that hash collision that could mapping to the same buckets. Yeah? So you have hash collisions, of course, and then you have two hash functions for different keys mapping to the same bucket. It could be that the point, whatever, 7, 8, set that bit. Now you're looking it up with 4.2. 4.2 was never inserted, but the bit is set. The only thing to learn here is, yeah, may be there. So I have to continue, but I can't be sure. Yeah? This is called a Bloom filter. We look at more details about Bloom filters next year, actually. And that's a lossy. A Bloom filter is a lossy bitmap index, in a way. Yeah? It's a form of compression. Yeah? There are other ways to compress bitmap indexes, and we will look at other schemes in January where you have a lossless compression scheme. This is a lossy compression scheme. It allows you to only use very few bits. Yeah? It's a very famous technique also in the context again of the simple version, yeah, differential indexing to check, okay, do I have to look in here, yes or no, stuff like that. So it's relatively easy to implement. And yeah, the implementation, that's what I'm doing here. It's actually a poor man's version. of Bloom filter. We have already a more evolved implementation of that, but I didn't want to integrate it now because I haven't explained it fully. That will happen in January. But you see it here, that's this crystal, so it's a very simple implementation here. Yeah, but basically you see the constructor, what's happening here, okay, I'm extending the buffered inner node now, implementing it on top. I say this Bloom filter has a certain size. It is a list of Boolean values. And what I'm doing is I directly initialize a list of this length, yeah, using this list comprehension of 142. Now I have my own hash function. I was initially thinking about using the inbuilt hash method in Python, but it really was misleading and didn't really work. So I had my own hash function here defined. So what I'm doing here is in the get method, I always consult first this Bloom filter. So if this bit is set, yeah, so it's a hash function, whatever that returns, modulo the length of this Boolean array. So if that is set, yeah, then we are in the space, oh yeah, maybe there, yeah, and then I'm going down the tree as before, or in this case I'm calling super, and super again is from the buffered node, and the buffered node will then check the buffers and eventually go down the tree again. Yeah? If not, okay, I'm sure I can return an empty iterator because it's guaranteed to not be there. Yeah? Fantastic. And the same happens in put. Yeah? That's basically where you can bump into these conflicts I just put on the blackboard. Yeah? So whenever you put something here, you make sure you update your Bloom filter. Yeah? So you run the key through the hash, modulo the size of the Bloom filter, and set it to true. Yeah? Right, and then again you delegate to the top level node. So it's just the only side effect of put is you maintain the Bloom filter. Other than that, you delegate to whatever the put method of the buffered tree was doing. Okay? Yeah, I think it makes sense that I think I have a visualization. I say here, right? This one. No? Yeah, it's a bit hard to see. Okay, but then you see basically. Okay, now you see all these structures. Maybe I can make this small. So basically here for the leaves, you see the list of vectors here. You see the buffer and the entries there. So this is a key, and this is a value, and then you see the Bloom filter. And of course, then you can come up with like a filtering property, and that's and I define it here like, okay, I mean the more bits are set to true, the less useful is this Bloom filter anyway. If everything is true, I can throw away the Bloom filter. Yeah? Ideally, this Bloom filter should be something like, oh yeah, I often hit into false, yeah? Because then I can stop my search at that point in time. And that's what I'm showing, what I'm using in the visualization here. Why did I do that? Crystal, buffer, X shift, int, commas. What was that? So here, that's this alpha, right? That's this alpha. It's basically the opacity. If it's set to 1, it's maximum, and if it's 0, it's nothing. And then basically, the highest usefulness, if everything is set to false, yeah, I draw it with alpha 1. Yeah, it's fully shown. But the more and more you keep on setting bits to true, the lighter the color becomes. And that's basically what I'm computing. So here I'm computing the number of bits that are not set, because the number of those bits define, or the number of those bits divided by the total size of this Bloom filter defines how this is visualized. And that explains in the visualization this effect you're seeing. Initially, when there's not so much data in the tree, so many bits are still set to false, so the Bloom filter has its purpose. Yeah, but the more you keep on inserting, the less useful it becomes because all of the bits were set. Yeah? So there are many, many things you can play with. So one important question is how to set the size of the Bloom filter. The Bloom filter should also be used with more than one hash function. We will look at that. So rather than when the key comes in, you just put it into one hash function, you put it into multiple hash functions, and the deal is then really all of those buckets have to be set to true to continue the search. And then you can compute, there's a formula for that that gives you the optimal number of hash functions. We'll look at that in January again. Yeah, that's basically this part. What else can I show? Yeah, I invite you to take a look at that. So it's really, I mean, to me it was really like I saw this in kindergarten and so on, but there's so many important indexing concepts you can explain. And in this lecture, we don't have time to get into details, but I hope now when you sit under the Christmas tree, you will remember this lecture and will, oh, Kendall, yeah, that's a buffer. Right, yeah, that's what I learned. This professor, yeah, right. Yeah, ISIM, yeah. Hey, mom, you did the ISIM property on the tree. That's fantastic, yeah. And the buffer burned down, right? I mean, shouldn't you refill it? And hey, there's this crystal balls. Hey, mom, you know about Bloom filters. That's fantastic, right? Yeah, that's so I hope you never forget this stuff anymore. Right, and there's a couple of tests again. I invite you to look at that. So we have tests for the Radix Trie. Still the breakpoint. I found a bug this morning. So if you update it before 9:45 today, you should pull again because when I did the bug fix. Yeah, again, we check number of configurations here. I think the Christmas tree test is a bit more evolved here. Yeah? So I check the different factories, whether it returns the correct results, blah, 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 and so forth. And again, because we were just discussing that in my group again. So that you have so many different ways to write a unit test. And of course, the textbook thing is, yeah, you put like 3 tuples into the index and then you think about corner cases and go through all the methods and you check coverage, tra-la-la-la-la-la-la-la-la-la. That's fantastic, but there's always one test you must do in databases, and that is stress test, whatever you implement, be it a join algorithm, be it an index structure. Yeah, it's kind of an end-to-end test. So basically it means you keep on adding millions of tuples into these indexes, stress testing them, hoping for the best. Yeah, because it often occurs that you thought about so much about the index, you wrote the perfect test, you thought you wrote the perfect test, yeah, and you added 1,000 tuples, then you keep on adding tuple 1001 and there's a bug that you overlooked. It's so easy to overlook these corner cases. So there should really be part of a unit test. It doesn't have to be run with every unit test, but could be a nightly unit test where you scale up your tests and run your structures with bigger data, because it allows you to find bugs in many cases. It's super useful. Okay, sure. That's what I wanted to show. So I hope you learned something and show that what you learn here at university to your parents, so you learn something useful. Yeah? Other than that, Merry Christmas, Happy New Year, see you in January. Yeah? Thanks.